I've given you access to a template that you can build components for a steam power plant for the semester project. This semester project will lead itself to a Thermo 2 semester project. So I want you to build the individual components, and we'll be putting things together eventually to make a steam power plant. So I'll need to open Excel, and when I do that, at the bottom here are some options. Can get that to move up a bit. So File, Open, and click on Options, and you want to choose the Trust Center settings, macro settings, and enable macros. So you'll need to do that in order for the functions to work. I have some macros that are set. When you're finished, you'll want to go back and turn those settings off so that if you open another spreadsheet that it's not running macros that you don't know about. So I'm going to open this spreadsheet, and I'm going to browse for it. It's on right over here to the left. And it should be here, right here. So semester project. So I open that, and some macros are enabled. The way you'll know the macros are enabled is if I change this value, it'll show values here. It won't just say value. All right, so this first tab, and I can close this. This first tab is just showing you how the functions work. So down here at the bottom, it shows you, different components. So there's other tabs, but we'll start on this water one. So if you look here, these are just numbers that are typed in, but down here it has an enthalpy of 3706.82, and there's a function that is typed in that cell. So the function is water, which I wrote as a graduate student many years ago, and it's from chapter 11 in your textbook, the fundamental formulas. So you specify the two properties that are given. So I'm giving temperature and pressure, and then I'm requesting that value for enthalpy, and then I need to tell the function where those values are. The value for temperature is first and the pressure is second. So the syntax for if you want to give temperature and volume, temperature and entropy, pressure and enthalpy, pressure and entropy, those are the options. And then you can request any of these, and they will give you, in general, superheated properties. One exception, if you have pressure and enthalpy, it can give you from compressed liquid all the way to superheated values. Over here on the right, if you specify just a pressure, you can get any of the saturation values and the syntax here. So if we look at HF, the function would be water, specify the pressure, or you can specify the temperature, and then what variable you're requesting, and then where is the value for the pressure. So here, if I double click this, you'll see it's giving this pressure. All right, so now that we know how to use the water function, let's start with the pump. So I'm going to click on the pump tab, and here is an example on the left with just values put in there. So you can see what the answer should be. And we're going to enter this, we'll enter the values over here. So let's start with the known values. So on the cells that have a fill of yellow means that those are not equations, those are just given values. So let's enter those. So this is state 8. This is 1000 kilopascal. This cell is 618.547 is our enthalpy. The entropy we're going to calculate, but the mass flow rate equals 100. The pump efficiency is 1. And I typed equal 100, you can just type 100. And the exit pressure is 12,000. Right, so now all the given values are input. Now we need to calculate things. So if I wanted to know the temperature, I could get that from the pressure and enthalpy with the water function. So I'll type equals water, specifying pressure and enthalpy. I want the temperature, and then I click the cell where the pressure is, comma, the cell where the enthalpy is, and end parenthesis. And it gives me the temperature, 146.802. We could check that in the tables. So at 1000 kPa, so 1 bar, so here at, 1 MPa. So at 1 MPa and at 618.547 is the enthalpy. Well, that's not superheated, obviously. So if we go to the saturation tables, and we go to 1 bar, and at 1 bar, we look at HF, and HF at, not 1 bar, but 10 bar, so 1 MPa, and we have 762.81, and ours is 618.547, so we're a subcooled liquid. So this pressure enthalpy is giving us the subcooled liquid value. So this is below the saturation or below the boiling temperature for 1000, and at 10 bar 179.9 is the boiling temperature, and we're at 146.8 degrees C. Let's just try a little change here. Let's make this enthalpy equal to 762.81. We get 179.9, so we just typed in the enthalpy for saturated liquid, and it gave us 179.9. Let's try an enthalpy of 2778.1. And we get very close to the same, 179.9, so it's thinking this is just a little bit superheated, so you'll find very slight differences. So make sure I typed in the right value, 2778.1, so just a little bit difference there. And if we go to the superheat values, and so 1 MPa, let's type 3178.9. And we get 360.228, so maybe 1 or 2/10 of a degree difference in the temperature. So we can use this function reliably. We won't get always exactly the same values as the tables. All right, but let's go back to, we wouldn't want to send superheated vapor into a pump, so 618.547. Okay, so back to our matching our values here. Now we can do the same thing, equals water, pressure and enthalpy given, comma, we want this time entropy, and it can be upper or lowercase, and then select the pressure, comma, the enthalpy. And then here we can specify this function equals, and let's look over here. The definition of quality is H minus HF over HFG. So I'm going to take this H as an input minus water. This time I'm going to specify pressures given. The value that I want is HF, and I'm going to specify the pressure. And then ends the numerator, the parentheses, divided by water, and this time specify the pressure again, but I want this time HFG. And then again I have to specify the pressure. And I get a quality of 0.0714. So all is good on this side. Now we come over here. There's a change in state, so I'm going to change this, add 1 to it. So this will be the next state in my system. So if this becomes a 6, then this will be a 7. Now this gets a little trickier. So let's look at the equations for a pump. I've got my inlet over here and exit over here. If the pump was isentropic, then the exit temperature would equal the inlet temperature. So let's start with assuming that it's isentropic, and then we'll put in our equation a way to adjust it if it's not isentropic. So the exit enthalpy, if it's isentropic, would be using the saturated liquid approximation, HF at the exit temperature, which in this case is the same as the inlet, plus VF at the exit temperature, which we're saying the exit will equal the inlet if it's isentropic, times P minus P sat at the exit temperature, or inlet, since they're the same. So let's just type that out down here. So I'm going to put HES equals, and we'll put that function in. So equals HF, I use the water function, water, and I'm going to specify the pressure, and I want HF. And actually I can do that at the temperature. It'll work either way, but it makes more sense to use the temperature, since that's how I have it written. HF at, and then the temperature. So I'm going to use this temperature because later this temperature will equal a different value. So use this one, which is really the exit temperature if it's isentropic. Okay, then plus my VF, which is water, specifying temperature, requesting VF, and then indicate where the temperature is, times my pressure, which is this exit pressure, minus Psat, so water again. I'm going to specify the temperature, comma, I want pressure. In this case, we don't type Psat, it's just pressure, just the way I decided to write the function. And then we specify where the temperature is. And then that needs a closed parenthesis. So this is HF plus VF times P minus Psat. And I get 630.507, very close to this one. So the slight difference there just happens to be a little, well, a few little differences in the way I calculated the solution. So some of the values aren't exactly the same in the solution. This was actually just slightly off on the temperature. So that is the correct value. And now I'm going to find the actual enthalpy, because it may not be isentropic. So I'm going to use this relationship, which makes use of an isentropic efficiency. So the if you solve for the actual exit enthalpy, so HE, so that would equal this, and actually instead of writing it here, let's just put it up here. So this is my exit enthalpy, and I'm going to write that it equals the inlet enthalpy, which is this one, plus this thing I just found down here, HES, minus the inlet enthalpy, divided by the pump efficiency, which is down here. Now it's 100% efficient, so it won't change the answer. So when I press enter, look at 630.507. Now what will change is if I change this number here, let's say to 0.9, then this value will change. So that's what I want, is that it accepts an isentropic efficiency. So let's not use this value. So I'm going to highlight that cell and copy all this, without the equals. Right click and copy. Of course you could type it again, and I'm going to hit escape, go to this cell, and so my I5 was that cell that I calculated there, but I'm just going to paste this in here. So shift insert. So that's just a little tough to type all at once, so just kind of broke it up, but if you want you can kind of write that down. So this is H inlet plus this long expression to get the enthalpy at the exit, which is this whole expression here, and then minus H inlet divided by the efficiency. So now this should work, and I can delete this. This is not really needed. And now if I change my efficiency, those values change. I'll leave it at 1 for now. Okay, so now I have pressure and enthalpy, so I can do the same thing I did on the other side, equals water pressure and enthalpy given, temperature, and the pressure is here, the enthalpy is here. Now I get the temperature. The entropy can be found the same way. Pressure and enthalpy, and entropy, specify those two cells. Okay, now there's a little shortcut you can use. This took a while to write, so I made a function that just has that built into the function. So, and I just called it x quality, and there's two parameters you give it. You give it the pressure in kPa and the enthalpy in kilojoule per kilogram, and it will give you the quality. Now, the quality is not really defined here, so it's below 0, but I went ahead and kept it because it gives me an indication of how far I am away from being saturated. So the more negative it is, the more subcooled it is, or more compressed liquid it is. So it's further away from the saturation curve. If it's greater than 1, then that's not defined still, but it will tell us then how far we are away from the saturated vapor curve, so how much we're superheated. So it's a nice little indicator, even though it's not standard. Okay, so now if I change this again to 0.9, or let's say 0.85, so if I have a pump that's not real efficient, what I noticed is it heats up a little bit, so it comes out at a higher temperature, and also the enthalpy is higher than it was otherwise, and so we would expect there to be a little more work. And then also the entropy is changing a little bit, so so we have a little higher entropy because it's not isentropic, so it went from 1.808 to 1.813. Okay, so let's go back here because that's what we have our values for, and then finally our equation for the pump work would be equal to m dot times, and we're going to write this as h exit minus h inlet because I want a positive value. So exit minus inlet. So since it says work in rather than just work, we're putting the direction here on the name of the variable. And I get something very close, again, the same for the same reason that this is slightly different, partly because this input value for these answers was a little bit different than 547. And now if I change it to, say, 0.85, all those values will change. So you can just make sure that if you put 0.85 here that you get all these values. And that would prove that you've typed them correctly. All right, so I hope this is helpful. Make sure you understand the equations for the pump and how we're doing this with spreadsheet. And I'm hopeful that you'll enjoy building this very complex, after we build all the components, analysis tool for designing very complex power plants in a very short time. Once you have these components, you can build this complex system in about 30 seconds.